Learning math is made easy, no more fear. Target online class, we got you. Wherever you want it from, we got what you need. Target online class.
Good day, viewers all over the world. You are welcome to Target online class. Today we want to look at the order. We are starting from the order of a group. We are starting from the order of a group. So as we have it on the board, the order of a group is the cardinal number of elements in G. That group is G. Is the cardinal number of elements in G. And it is denoted as, just like where we have the absolute value, G inside. So that is the definition of the order of a group. And there's this other one called the order of an element. There are two different things. The order of a group is different from the order of an element. Please, let's get the difference. Let's get the difference. The order of a group is the cardinal number of elements in a group. Just like when we talk about the cardinality of a set. So when we talk about the cardinality of a set, for instance, if you have a set, let's say set A that has elements 1, 2, 3 at the elementary stage, then n of A will be 3. So the cardinality of a set is the number of elements in the set. So it's the number of elements in that set. So at the elementary stage, if you have a set A that consists of 3 elements, 1, 2, 3. So the cardinality of that set will be represented by n of A is equal to 3. So in this case also, we are talking about a group. You know, of course, you know that a group is a set with a binary operation. This G simply means a set, a non-empty set G that has a binary operation. Asterisk. That is, that binary operation must satisfy 4 conditions. This non-empty set must elements inside this non-empty set must satisfy 4 conditions. It must be closed, it must satisfy associative property, existence of identity elements, and existence of inverse elements. That makes it a group. So in this case now, if you want to find the order of a group, the order of a group, G, in this case the group is G, is the cardinal number of elements in G in that group. That is, it is denoted as this symbol, like when we have absolute value. You know, in mathematics, when you have something like this, maybe it simply means that you disregard the negative sign. That's absolute value. So that is the definition for the order of a group. And this order of a group is simply means the number of elements in that group. That's the meaning of order of a group. So if you are to define the order of a group, that is how to define the order of a group. Okay, then let's now move to the order of an element. Of course, a set, a non-empty set has at least one element. Let's say you have a set A that has 1, 2, 3. All these elements, 1, 2, 3, they belong to this set A. Of course, there's a way we write it. You can say 1 belongs to A. Okay, we can say 2 belongs to A. 3 belongs to A. 1, 2, 3 are elements of that set A. Now we want to talk about the order of an element. An element belongs to a group. So how do we define the order of an element? That is what I'm about to do now. The order of an element, say A. In this case now, A is an element in G in that group. The order of an element, say A, is the least power or multiple of A, of that element, that gives the identity element. Please, I want us to note too, if you are to define the order of an element, in terms of a group, the order of an element, say that element is A, is the least power or multiple of A that gives the identity element. So under the order of an element, this is what you do. So that is the definition. If you are to define the order of an element, just give us this definition, that the order of an element, say A, you can use any letter, but we know we represent elements with small letters, and that's set with capital letter. Okay, if that is the case, then the order of an element, say A, is the least power or multiple of A that gives the identity. So now let's see. That is, I want to expatiate further. That is, let A be an element. Let A be an element. Let A be an element of a group. Of a group, say G of a group. It could be any group. And E, the identity element. The identity element of the group. So if we now have n that belongs to a natural number, such that, now let's note these two properties, because in the definition of the element of order of an element, we have it to be the least power or multiple. So let's see the implication of power and multiple. Let's see the implication, such that Roman figure 1, where we have A raised power n is equal to E. This is when we have power. And for any element m that belongs to n, if you can have A raised power m is equal to identity element, then n is greater than or equal to m. Then the second condition, where we have na is equal to identity, and for any element m that belongs to n, if you can have n ma that gives identity, then n is less than or equal to m. Now let me explain. You know, in the definition of order, the definition of order of an element, we say that the order of an element is the least power or multiple of A that gives the identity element. So we are trying to explain now that if A is an element of a group, then E is the identity element of that group. Okay? By now we know the meaning of identity element. It varies. Under addition, the identity element is 0. And under multiplication, the identity element is 1. Identity element simply means a neutral element. That's the meaning of identity element. Element that you relate with, that nothing changes. So in this case now, look at the first question. If it is in form of a power, this is the element. Raised power n gives us identity. And if we have another number, say m. A raised power m gives us identity. It simply means that this n can only be less than or equal to m. It cannot be greater than m. And in case of multiple, this is multiple. Multiple simply means what you use to multiply a particular figure. And when you use it to divide it, it's without remainder. For instance, the multiple of 3 are 6, 9, 12 in that order. So in case of multiple, n a must give us identity. And for any m that belongs to n, this is the condition that we have. So I'm going to use example. To explain this order of an element very well. So in this case now, we now say that n, from here we say that n is the order of A. That is, it is this n that actually give us, when it is power or when it is multiple, it is this n that will give us identity. Once we are able to use it, if it's in form of a power and we get the identity element, it shows that this n is the order of A, is the order of that element. That's the meaning, that is the interpretation of order of an element. Now please note what I'm about to say. Note that if this either power or multiple does not exist, in case of the order of an element, it simply means that the order of A, that element, is 0 or infinite. If you use the power and it gives you identity element, or the multiple and gives that, if these two conditions does not exist, the implication is that it simply means that the order of that element, in this case A, is said to be 0 or infinite. Now let's see example. I want us to see example on this order of an element, so that I will use this example to buttress my point, so that you understand it better. Let's see example. Let's see example on the order of an element. Consider G, which is equal to 1 minus 1 I minus I. Okay, and the group G with identity element multiplication, with binary operation multiplication. The question now says that we should find the order of each element of G. So this is what we want to do. Look at the element of G that we have. There are 4 elements there. 1, -1, I, and -I. So, and the group is G. This group is G. The binary operation in this group is multiplication. Okay? So we want to find the order of each element. This is one element, this is another element, this is the third and fourth. So how do we do that? Because we are under multiplication, please let's note. Because we are under multiplication, the identity element will be 1. Please, I want us to note, these are important concepts that you should know at this point. The identity element of multiplication is 1. If what you have here is addition, the identity element is 0. So please let's note, that's the first condition. So what do we do now? We want to find, we have to find the order of each element of G. There are 4 elements in G: 1, -1, I, and -I. So we know the identity elements. You know, there are 2 conditions. Is that AN is equal to identity element, or NA is equal to identity element? That is, either we have the power or the multiple. That's where we get what we talk about under the order of the elements of a group. So now let's see what we are going to do. So for 1, so we want to see the order. For 1, this is the first one. For the first one now, 1. For 1, what do we have? 1. Of course, if you find 1, in case of, I want to use the power now. 1 raised to power 1 is 1. 1 raised to power 1 billion is 1. So we are going to get 1. Irrespective of the power, it's going to give us 1. So we say that the order of 1 is 1. That is for 1. There's only one thing that we can get. Then for -1, what can we get here? When we say -1 or raised to power 1, -1 raised to power 1 is going to give us -1, right? But if you say -1 raised to power 2, we are going to get the identity as 1. So in this case now, the order of -1 is 2. That is the power. Please, I want us to please look at it very well. Look at it very well. In the first case now, when we have 1, irrespective of what we use, we know 1 is an identity. So if you say 1 raised to power 1 million, it's still 1. So that was the reason why we said the order of 1 is 1. But in the situation whereby we have -1, what happened? -1 raised to power 1 is -1. But if you say -1 times -1, are we not going to get the identity? We're able to get 1 because the power here is 2. Then that is why we said the order of -1 is 2. So do you understand how to find the order of an element now? Please just comment at the comment section. Let me know if we are on the same side. Please comment. If you understand what I've done, just comment and let me know that we are on the same page. Okay, we now move to the third element now. We move to the third element. So let's move to the third element. That is for I. So what will be the order? Of course, in complex number, we know that I is equal to square root of -1. Then I squared will be equal to what? -1. That's what we know under complex number. You must have done that. Complex number. And if you don't have idea of complex number, just check my videos. I have videos on complex number, so you can check that. You can check my videos on complex number. For I, what will happen? So I raised to power 1 is 1, but I raised to power 2 will be equal to -1. I raised to power 2 is -1. but the order, the identity elements under consideration is 1. So how do we get that? But if I raised to power 2 is minus 1, the minus times minus will be plus. Then this is what I will do. I will say I raised to power 2 multiplied by I raised to power 2. That is I raised to power 4. It's going to give me 1. That's when I'm going to get that 1. Please look at minus, because I raised to power I squared is minus 1. So minus times minus is plus. Then if I say I raised to power I squared times I squared, that's I raised to power 4. It's going to give me 1. In this case now, the order of I is 4. It is the power that we are using to find the order. The power. So I want you to understand the definition. Then the last element is there for minus I. What will be the order under minus I? I think for minus I times minus I. Minus times minus is plus. It's going to give us I squared. And I squared is still minus 1. So in this case also we are going to have I squared times I squared. And that will be I raised to power 4. That is the one that will give us 1. So the order in this case, the order of minus I is also 4. So that is how to find the order of elements of a group. So you can just go over this over and over again in order to be able to know that. So let me introduce Lagrange theorem. We still have so many things to discuss. So we take it one after the other. So let's introduce Lagrange theorem. The theorem states that if H is a subgroup of a finite group G, then the order of H divides the order of G. That is the order of H. That is the order of H. You know, this is the order of H. This is the order of H. Okay, that is how we look at. That's what we are saying. That the order of H divides the order of H divides the order of G. That's what we have. So please let's look at that theorem very well. It has to do with group and subgroup. So the Lagrange theorem states that if H is a subgroup of a finite group G, then the order of H divides the order of G. That is what we have. So how do we prove this theorem? Of course, for us to be able to prove this theorem, there are about 6 steps that will follow. How do we prove this theorem? So since we are talking about the order of H, that's H is a subgroup, so it's a group. G is also a group. So you know there's a difference between the order of a group and the order of elements. But every group has an element. So we are going to use the knowledge of the order of elements to be able to prove this problem. So this is what we do. We say under the proof, we say let M equal to the order of G and L equal to the order of H. That is where M is the element under G and L is the element under H. Then what will happen? We now say that each coset, of course we know the meaning of coset now, each coset of H in G, H is the subgroup of the group G, contains L elements. Since for all G that belongs to the group and H prime. These are elements of H. Belongs to H, the subgroup. We can have GH to be equal to GH prime. That is, H is an element of the subgroup. H prime is also an element of the subgroup. So we can have that. It is possible to get that. And if you can have that, we are going to use the law of cancellation. Law of cancellation. This implies that H is equal to H prime. How do we get that? We use cancellation. Cancellation law. Cancellation law. That's how to do that. If G is equal to G H prime, then we are going to use cancellation law to be able to get that H is equal to H. Now we now conclude. We said thus each element of a coset is disjoint. Is distinct. No, not this. Is distinct. That is, when we discuss cosets, we talk about coset being either right or left. So it can be either right or left when we discuss cosets. So each element of a coset is distinct. So please let's know that. So let's note that. Then from there we can actually continue. Then we can say that all the cosets of H in G forms a partition in G. That is, this is what I'm about to say. From the proof now, we have been able to establish that each element of a coset is distinct. So since we have been able to establish that, then we can make this assertion that all the cosets of H in G, H is a subgroup of G, form a partition of G. So it's from a partition of G. So please, let's note that. So if that is taken, then we can let K, this is also an element too, let K be equal to the number of distinct cosets of H in G. Yesterday in our last class, when we talk about coset, we talk about the index of that coset. That is, the index of a coset is the number of distinct elements that we have in that coset. And we are able to, when you go through the example, we are able to show if there are some that we have just two. In the situation where we have 0, 2, 4, and maybe 1, 3, 5. They can be repeated when we test the elements, all the elements of a group in with this subgroup. So these are the distinct elements. So let K be equal to the number of distinct cosets of H in G. Then since this form a partition, it simply means that this is what we are going to have. The union of from I to 1 equal to M, we have Gi to be equal to H. That is, this is going to give us G. When we talk about partition simply means when you partition a place into several particles. For instance, we can have something like A union A1 union A2 union A3 union ... union AN. So I can, when you say partition, it simply means that when you combine all this, let's say this is a set, and you partition this is A1, this is A2, this is A3, up to AN. That's the meaning of partition. So the subset here, the subgroup are partitioned in that concept, are partitioned to form a group. So I can write this. If I don't want to write all this story, I'll just say the union I to 1 to N AI. That's how to rewrite that. When you have a partition, you can rewrite what I have there. So that's how to rewrite it. You just write it. So in this case now, what we have there, simply means that these GI are elements of the group. You know, when you say coset, this in this case now is right coset. So what we have there simply means that we can have G1H union, we can have G2H union, we can have G3H up to when the value, the last value is M, and that is the meaning of this. So we are saying that the coset, that coset of H in G forms the partition. This statement now, this is the interpretation. All the cosets of H in G forms a partition of G. This is the interpretation of this statement. This is the interpretation. And if that is the case, and forms a partition, then once they form a partition, it simply means that GIH intersection GJH will be equal to empty for I not equal to J. What is the meaning of that? That simply means that the intersection of each element here is disjoint. That is when you take the intersection of two elements and it's empty, it simply means that the two elements have nothing in common. Because we are talking about partition, they belong to various group. They belong, when you say partition, it's different, nothing in common. But addition of everything now, the union of everything give us this G. It simply means that none of these elements here, say G1H, G2H, when you take the intersection, it will be empty. So when you take the intersection of two sets and it give us an empty set, excuse me, it simply means that the two sets are disjoint. That is the interpretation of what we have there. So you don't need to cram anything. We can actually this thing can actually come out straight. So we now just does the summation now, the addition of everything. K n of GH will give us, this will give us it's going to give us the order of that element. So we can say maybe alpha from 1. So this will give us, this will actually give us, it's going to give us the order of that element, and the order of that group. This is the order of the group. That's the implication. But we must note that each coset of H is equivalent to H. So please let's note that each coset of H is equivalent to H. So let's note that each coset of H is equivalent to H. Then if that is the case, then this is what we have. If that is the case, we are going to have NGH. This is the coset of H. It will be equal to NH, and that will give us L. That is defined as L. Okay, that's what we have. So that's what we have. Therefore, we can conclude that K, we have defined all this from the inception. Ng of H, coset of H, is same thing as K into bracket the order of the subgroup, and this same thing as KL, that's the order of the subgroup, which is same thing as the order of the group. That's what we are going to have. This implies that KL is equal to M, because the order of this group is defined as M from the inception. That's what we have. That's what we have. We now say since L divides M, since L divides M, therefore N of H divides N of G. And that's this same thing as the order of H being divided by the order of G. And that is the end of the proof. So please just try and go through the proof over and over again for you to be able to have a proper understanding about the proof. So just try and go over it. So to be able to have proper understanding about what you have there. So then After this, let's just define a normal subgroup. Let's define a normal subgroup. Let's define a normal subgroup because over time. Let's define a normal subgroup. How do we define a normal subgroup? A normal subgroup. So how do we define a normal subgroup? So we say let G be a group. Before we talk about subgroup, we must have a group. And N a subgroup of G. And N a subgroup of G. Then N is called a normal subgroup. A normal subgroup. N is called a normal subgroup or an invariant. An invariant subgroup of G. So is that you call it a normal subgroup or an invariant subgroup? Is that normal, or is that you call it normal or an invariant subgroup of G? If the right coset of N equals the left coset of N for each element of G. That is, if you have Gn right coset is equal to Ng for all G that belongs to a group. Now look at, when do we have a normal subgroup? We have a normal subgroup in a situation whereby you have a group G and you have N as a subgroup. So N is the subgroup. So then when we talk about cosets in the last class, we realize that we pick each element of a group operating with, we said something like this, we said G of H. This is the right, such that H belongs to H. This is what we have. So this is what we have, and that's what we discussed yesterday. So in this case now, for us to be able to have a normal subgroup, the right coset of N must be equal to the left coset. So either you find the right coset or the left coset, you must get the same answer. And that is what we call the normal subgroup. That's what is called the normal subgroup or an invariant subgroup. That's what's called normal subgroup or an invariant subgroup. And of course, there are examples here that we can actually show. I have a question here that says that we should show that every subgroup of an abelian group is a normal subgroup. So there's this interesting question here. So let me just solve this, then we close for the day because of our time. So let me solve this. Let me solve this important question. So let's solve this important question. Let's solve this important question. Let's solve it as example that show that every subgroup of an abelian, of course, abelian simply means commutative. Abelian group simply means commutative group. Once you have divided a group and add commutative property to it, you get an abelian group. It's a normal subgroup. It's a normal subgroup. So how do we show this? What is the meaning of normal subgroup? Normal subgroup simply means when the right coset is equal to the left coset. That's the idea about normal subgroup. Once there's equality between the left and the right coset. So how do we approach it? We say let H. So yeah, we say let H be a subgroup. Let H be a subgroup of an abelian group G. Okay, this implies that for all H in that subgroup of H, we have H that belongs to G. That's what we have. So this simply means that H is a subgroup of G. Okay, that's what we have. Then this also implies that for all H that belongs to H and G that belongs to G, we have HG that belongs to G and G inverse that belongs to G. Please let's look at it very well. Let H be a subgroup of an abelian group H. Of course, we gave a condition yesterday that the element that we have in a subgroup automatically will be in a group. If you check what we discussed in the last class, we have established that fact. So if H belongs to H, H can also belong to G because H is a subset of G. So a subgroup is a subset of that group. For you to be able to have a subgroup, that subgroup must be a group. So it's a subset of that group. Then this is what we have. From there now, we have that G inverse is equal to G inverse H. That's what we get. Then this implies that G inverse is equal to H. If we rearrange, that's what we are going to get. So that's what we are going to get. Then thus G inverse is equal to H for all G that belongs to G. Therefore, H is a normal subgroup of G. And that's what we are going to get. Because here, in this case, we have G inverse to be equal to EH before this step. And that is what we are going to get. So I'd love to stop here. Because of our time, by the grace of God, we are going to continue from there. Thank you, and God bless you all.